This is a short presentation understanding QoS across networks including IP, MPLS, and SD-WAN networks. Part of an enterprise sales upmargin acceleration presentation and program designed to reduce the sales cycle, increase competitive edge, reduce staff turmoil and turnover, produce higher margins, provides improved sales leadership across many markets and technologies. This is available after ITexpo at your location, anywhere, anytime, to get certified sales smart. Let's begin by looking at the OSI model, Open Systems Interconnection model. The model was really designed to provide open communications between different kinds of mainframe networks, basically adopted by the internet for wide-ranging devices, applications, technologies, and more. When you look at the way the thing fits together, it fits together quite nicely. Applications at layer 7. Layer 6 is presentation, which is basically a control layer. Layer 5 is session layer, and basically think of that as session initiation protocol used in VoIP. Transport layer, TCP, transmission control layer at 4. Layer 3 is IP or Internet Protocol. Layer 2, Ethernet, and MPLS. MPLS is a shim or an add-on to the IP packet to provide for QoS. Layer 1 is really for optical, fiber, copper, and wireless communications. The way this thing fits together is very complicated, but the idea of the internet was basically an open model where we can have different kinds of technical applications supporting different kinds of user applications such as voice, video, text, and other technologies. These Ethernet at layer 2, which is the protocol of favor for cable TV operators, your wireless, your Ethernet connection on your laptop or device. And really, Ethernet is really designed for connecting different kind of networks together, and really provides no real quality of service. It basically floods the network and provides for communications, but on the other hand, it really doesn't in managing a complex network. IP at layer 3 or IP version 4 here is shown, and IP does have a type of service or quality of service bits, TOS or diffserv. And at the same time, unless the router recognizes these kinds of packets, then there's really no quality of service. And so it was never really adopted across many kinds of networks. The opportunity here is that to look at the beginnings of quality of service through diffserv. Differentiation services mark these bits for special routing. Again, the other router at the next destination where it gets connected has to recognize that types of service. Adopted. The major protocol that was adopted was Multi-Protocol Label Switching, or MPLS, and here's what it looks like, and here's what gets attached to the IPv4 packet. It's considered a shim or add-on to the packet and provides limited but also a number of bits, as you can see it towards on the left-hand side. The MPLS label of 20 bits can provide a wide-ranging use of applications. How it kind of fits together is that unless IP routers recognize either the TOS or MPLS, they route as is, sometimes called best efforts, with hot potato routing to get the packet off the network as fast as you can. Again, the IP networks really weren't designed for all the things that we use it for today. However, how MPLS works together, MPLS enabled routers use labels to determine the quality of service for each route. Crossing multiple carriers, the label priority is swapped to the next carrier, such as voice, video, email is shared across, ensuring priority across the edge of the network until the label is removed. It is the only really way we can do this, except for providing improved quality of service at layer 2, and that's where SD-WAN fits in. Here's where you have different kinds of labels for different kinds of applications. And at layer 4, transmission control protocol, again, was really not designed for quality of service, but basically for error checking. When I send my packet to you, you confirm that you got it. If you didn't get it, you send an indication through TCP that you need to send that packet. Here's another version of IPv6, which is being adopted but hasn't really achieved full force in the marketplace. There are other kind of packets out there called RTP. RTP is used for VoIP or SIP, Session Initiation Protocol, and it is really designed for ensuring, again, a kind of quality of service network. Here's your kind of Hollywood Squares approach to this whole process. I'm not going to go into details of this. You can look at it at your leisure. But again, we're really trying to figure out how can we do quality of service across different kinds of networks and different kinds of ways to handle both, again, incremental bandwidth allocation, support burstable speeds, queuing, shaping, policy. Some people call it provisioning, shaping, orchestration, and auto reroute. So again, when you look at MPLS, it really becomes the flavor square of choice here in providing for quality of service across networks. Again, this is a quick review of the different kinds of protocols we see across networks and the different kind of networks at layer 2, such as optical fiber, ATM, which has never really took off, but Ethernet really has taken off at layer 2. And we see layer 3 of MPLS and helping IP to provide that. But again, if the routers don't support or recognize the MPLS labels, it really doesn't do any good. Typically, you find in most kind of VoIP applications, streaming, etc., they use UDP or User Datagram Protocol rather than TCP, again, which confirms, did you get it? You got it? Send it again if I didn't get it. So you see the different layers, upper layers, such as SIP, and different kinds of that exist. Meanwhile, back to the basics of SD-WAN. In the beginning, local networks or LANs connected all your office data devices, sometimes called endpoints, together via switches to connect your local computer server where your office applications were processed and stored. Then wide area networks or WANs connected your office via routers to data centers or clouds where your website might be hosted and connections to the internet. The internet is also defined as the interconnection of networks. Networks grew as more routers and switches were required to make all the connections to different data centers, your home, offices, smart devices, and things like that. As networks grew so complex, they were harder and harder to manage with all the routers and switches. Again, where we look at these, how these fit together, buildings and office are connected together with optical copper wires such as cable TV, twisted pair, and wireless connections that have different bandwidth speeds at data center. Bandwidth is measured in bits, a 1 or 0 per second, such as megabits per second or millions of bits per second, or Gbps or gigabits, billions of bits per second. You only pay for the speed you need, but some providers offer other service options. A data center is a building, also called as a colo or co-location center, where networks are connected together inside a data center. There are computer servers, also known as CPUs, which host websites, provide application support, perform backup and storage, and other services. These servers are contained in separate cages for security to keep one company's equipment separate from another. To connect one data center to another, there are routers which direct or route packets called IP, data bits from one cloud or network to another, allowing you to send email, pay bills, back up your data, and operate your data system. A data center may be also a cloud. Cloud computing means that your computer servers and business applications, from word processing, billing, order, managing your website, finding products, ordering a pizza, grocery delivery, and more, can be connected together via routers. There are thousands of clouds supporting millions of websites. Clouds are also connected via routers, as one cloud does not host every website or application. There are many specialized applications of clouds, such as private, hybrid, or shared, or public. Companies often want private clouds for security, performance, management, and other reasons. Connecting all these clouds together are data centers with computer servers, data storage, your pics, videos. Also, Instagram and streaming, such as Netflix and iCloud, is getting rather complicated. There are two kinds of equipment, again, used to make the internet together, routers and switches. Back to basics. In simple terms, you're traveling, and if you change planes on the same airline, train, or even package delivery service, that's called switching. If you change to a different airline, that is called routing. Background switching is easy, but routing can be very complicated. It requires more management. Routing requires knowledge of other airline network, or in this case, internet carrier provider. That is, you need to know if the network goes where you want to go or publishes where they go, and what kind of services that other airline or cloud can provide in case you need to make a video call. Here's where the technology fits in. Routers are expensive and complex to manage, but switches are not smart and just connect bandwidth pipes or connections together. If you have a network of 10 or 100 routers, that means a lot of expense and time to manage all of them, such as truck rolls, on-site visits to make changes. With switches, it is easier, but may require more bandwidth to provide higher performance. A new concept called SD-WAN, or software-defined network, has emerged that is designed to eliminate much of the costs associated with routing. A cloud network would have fewer routers with switches used to provide the majority of data services, such as voice, video, streaming, etc. One of the advantages of SD-WAN, which is called a control plane, a level of management, is software-defined to look ahead like air traffic control to see the status of other switches to optimize flow and provide traffic management. One final point is that SD-WAN works within your own corporate network. However, when you cross-connect to another network, you need to connect them via routers. Here's a few last points of this. I know we tried to make this simple, but the idea is that if you're serious about SD-WAN, software-defined networks, here are some of the technical benefits. Improved quality service, built-in on-demand and dynamic traffic performance. Provide new ways to manage platform APIs or application programming interfaces. Integration for carrier network operation integration. Route management, enhanced component diagnostics and troubleshooting. I wrote a paper on this on SD-WAN and how it fits into AI. There are certainly the possibilities that AI will have a role in how SD-WAN networks are managed in the future, including such as disaster recovery, provide resilience, auto reconfiguration for man-made crises and natural disasters, security, no absolute security, but fast response to and management of security crisis mitigation, technology, new approaches to chatbots, voice digitation, call routing, and more. Here's a few more applications we go through these things. There are lots of them. Device management, migration to server and network virtualization accelerates BYOD or bring your own device provisioning. Management first and then provide scalable growth for customer applications. Cost, and this is where it really kind of makes the simple work, is that cost fewer boxes and lower layer interfaces, and staff consolidation, reducing duplications and inefficiencies. Agility on demand, network shaping, orchestration and provisioning, improved traffic capacity forecasting and physical plant geoforecasting, strategic design, test, and build new simulations and data visualization systems, and change algorithm models for evolving business applications. I'd like to thank you for taking a few minutes with us today and let us show you how good you really can be, and please consider our class for your next event. Thanks again.